Previously, we looked at using our rectangular coordinate system to graph or locate a point in a plane. In this section, we're using our polar coordinate system to locate a point such as P in a plane. Now, in a polar coordinate system, we have a polar axis instead of our x-axis. And our polar axis is just a line segment. So here, this point O is our origin or our pole, and our directed line or line segment is going in this direction. So this is our polar axis. Our point P is our distance from our origin or from our pole. So and this is our directed distance from our origin. Theta, our angle, is the angle from our polar axis to the terminal side. So theta is also our directed angle. To locate our point P in our polar coordinate system, we use the radius r and we use our angle theta. Here to demonstrate this, we have 3 points on our polar coordinate system. Our first point here has a radius of 2, so here's our origin, and you can see if we follow this around that our radius is 2. So this point is 2 units on the terminal side of the angle, which is 5 pi over 6. So if we measure it from 0, this direction, this is 5 pi over 6. Here for this point, our radius is 3, and this is on the terminal side of our angle, which is 5 pi over 4. Here for this point, we have 4 and negative pi over 3. So once again, our radius is 4. If we follow our circle around, we see that our radius is 4. If we go in this direction, we have 4 and negative pi over 3, because in a clockwise direction, our angles are negative. Or we could have written this as 4 and all the way clockwise, it would be 5 pi over 3. With our rectangular coordinate system, each point has a unique representation. This is not true in our polar coordinate system. Here we have this point r theta. We can see that if we were to rotate this point around, so this is our theta, if we were to continue around, then we still have the same point. The radius is still going to be 2, and our angle will now be, so we still have our same radius, and this will become theta plus 2 pi since it went around 1 revolution. We can also continue around a second time, and we have a second representation r, and now we have theta plus 4 pi. And we could continue around again until we have theta plus 6 pi and theta plus 8 pi and so on and so forth. Or we could go the opposite direction, and then it becomes theta minus 2 pi or theta minus 4 pi. So we can see for just this single point here, it has an infinite possibilities, not just r theta. We can rewrite this as having the same radius, but now it will be theta plus or minus, since we can go in both directions, and 2n pi. 2n pi means we have multiples of 2. So 2 pi, where n is an integer, so if n is 1, this becomes 2 pi. If n is 2, then this becomes 4 pi, 6 pi, and so on. So here we're changing our degree. Recall from just now we said that r was a directed distance. If we move our distance in the opposite direction, this now becomes a negative r. So if we have negative r and we add this is our angle theta, and we add pi to theta, it will take us back to our original point. So negative r and theta plus pi will take us back to here. So for this, we could say this would be negative r and theta plus or minus, since once again we can go in both directions. And this time we're going to say this is going to be 2n pi plus 1 times pi. It's an n. And this will give us odd multiples of pi. So 1 pi around, 3 pi around, 5. So if we have negative r and we had 1 pi, we go back to here. If we have negative r and we have 3 pi, it's going to be 1 pi, 2 pi, 3 pi back to here. If we had 5 pi, 2 pi, 4 pi, and finally 5 pi back to that point. So if we change only theta, we're going by 2n pi, and if we change r, then our angle is going to change by 2n pi plus 1 times pi. In this example, we're going to plot a point given in polar coordinates. We're also going to find two additional points or two additional representations of that same point. And our constraint is that the new point must be between negative 2 pi and 2 pi. So here is our original point, 3, and our angle is 5 pi over 4. So our radius is 3 and our angle is 5 pi over 4. When we plot this on our polar coordinate system, we have a radius of 3 and our angle is 5 pi over 4. This will be 0, pi over 2, pi, and 3 pi over 2. So our angle here is 5 pi over 4, measuring in this direction. So this is our 5 pi over 4. Now to find two additional points, we can use our formula. We can use this formula here, which says it's r plus theta plus 2n pi. Now if n is equal to 1, then this becomes plus or minus 2 times 1 times pi, or just plus 2 pi. Now if we add 2 pi to this angle theta, it's going to take us outside of our restriction. So we can possibly minus 2 pi instead, since this is plus or minus 2n pi. So now we have 3, 5 pi over 4 minus 2 pi, which gives us 3 and negative 3 pi over 4. So here is one of our additional representation of the same point. And we can prove that this is also represent the same point. So if once again we have our radius, which is 3. Our angle is negative 3 pi over 4, which now means we're going in a clockwise direction. So if we measure 3 pi over 4, we will see that we stop here. So negative 3 pi over 4 is the same thing as 5 pi over 4. So it takes us back to the same point. So this representation is the same thing as this. To find our third or second additional representation, we're going to use this formula. Negative r plus theta plus or minus 2n pi plus 1 times pi. Now here we're going to use n is equal to 0. If n is equal to 0, this goes away, because it's 2 times 0 times pi. So now we have 1 times pi, so it's going to be plus or minus pi. Once again, if we add pi to theta, which is 5 pi over 4, it's going to take us outside of our constraint. So we could subtract pi instead. 5 pi over 4 minus pi will give us pi over 4. So now we have negative 3 and pi over 4. So this is our second additional representation of this. And once again, we can prove that this is true. If we measure angle pi over 4, which will be in the first quadrant, so this is our angle pi over 4. So our r will be in this direction. Because it's negative 3, it's now flipped it over in the opposite direction. So pi over 4 and negative 3 moves it back to here. So all three coordinates represent the same points. To find the conversion from polar coordinates to rectangular coordinates and from rectangular coordinate system to our polar coordinates, we can superimpose our polar coordinate system on our rectangular coordinate system. So here our x-axis is our polar axis, so this is sitting on top of this, and here we have our y-axis. From this we can see that from our trig function, if this is x and this is y, then x would be equal to r times the cosine of theta from our identity that cosine is equal to x over r, or cosine is equal to adjacent over hypotenuse. We can also see that y is equal to r times sine theta, since sine is equal to y over r, opposite over hypotenuse. To go from rectangular to polar, we know that the tangent of theta is equal to y over x. So then we can take the tan inverse of y over x to find theta. To find r, we know that r squared is equal to x squared plus y squared from our Pythagorean theorem. So to find r, we would have to take the square root of x squared plus y squared. So here we can go in from rectangular to polar, and here from polar to rectangular. Here we have an example of converting polar coordinates to rectangular coordinates. First, we're given a radius of -1 and an angle of 5 pi over 4. So this is our r and theta. We know to convert from polar to rectangle that x is equal to r times cosine of theta. So here we have -1 times the cosine of 5 pi over 4. We know that the cosine of 5 pi over 4, which is in the third quadrant, is negative square root of 2 over 2. So now we have -1 times the negative square root of 2 over 2, which gives us a positive square root of 2 over 2. To find y is equal to r times the sine of theta. Sine of theta in the third quadrant is the same thing as cosine, so it's negative square root of 2 over 2. So -1 times negative square root of 2 over 2 gives us a positive square root of 2 over 2. So our rectangular coordinates for this polar coordinates would be square root of 2 over 2 and the square root of 2 over 2. Here in part B, we're given that r is equal to 5.4 and that our angle theta is equal to 2.85 radians. Once again, we're going to say x is equal to r times cosine of theta. So this is 5.4 times the cosine of 2.85 radians, which comes out to be -5.17 approximately. To find y, use the formula r times sine theta, and that comes out to be approximately 1.55. So our rectangular coordinates for this second polar coordinates is -5.77 and 1.55. Here's an example of converting rectangular coordinates to polar coordinates. Our rectangular coordinates given is -4 and -3 as our x and y value. So to convert it to polar coordinates, which is our r and theta, we need to find r and theta. We know that r squared is equal to x squared plus y squared. So r squared is equal to -4 squared plus -3 squared. So this becomes 16 plus 9. So to find the square r, we take the square root of 16 plus 9, which gives us 5. So our r value, or radius, is equal to 5. To find theta, we know that tan theta is equal to y over x. Our y value is -3 and our x value is -4. So theta would be the tan inverse, or arctan of 3 over 4. The arctan of 3 over 4 is 0.64. You know, our values here for our rectangular coordinates is in our third quadrant. So theta here is in our third quadrant. So to find actual theta from our polar axis, we need to add pi to this, or 3.14. So 3.14 plus 0.64 will give us theta, which is equal to 3.78. So our polar coordinates for this would be 5 and 3.78.